Welcome to Tumbling Asteroids and Young Earth Creationism. May it please you. Throughout our solar system, but especially in the region between Mars and Jupiter, orbit a vast number of asteroids. You can think of these minor planets as leftovers from the accretion of the major planets. Asteroids are so small that when viewed in a telescope they appear as mere dots, and hence the name asteroid, which means star-like. However, unlike actual stars, they are orbiting the Sun, so these dots will move through a long exposure image, leaving a streak. And this is how asteroids are discovered and how their orbits are determined. In recent years, we've been privileged to see a few asteroids up close, thanks to various spacecraft missions. They turn out to be rather bizarre little worlds with irregular shapes. Unlike the major planets, asteroids are not big enough for gravity to have been able to force them into more or less spherical shapes. They are typically covered with craters, indicating a violent collisional history. People are interested in asteroids because, as primitive leftovers from planetary accretion, they can tell us a lot about how the solar system formed. Meteorites are little asteroids that fall to Earth. They are the little siblings of a family that spans sizes from hundreds of kilometers to the microscopic. Even a very small meteorite can put on quite a fantastic show. Look out! And each one that falls from the sky is simply another little increment in the ongoing accretion of our planet. In fact, Earth puts on thousands of tons of weight each year due to this process. Fortunately, only very rarely are these baby asteroids large enough to be able to cause much of an effect on Earth's surface. In the tens of meters size range, they can pack quite a punch. In the kilometer size range, they might well have been responsible for mass extinction events.
Come on, dude, get to the point!
Be patient, we'll get there. As an asteroid moves through the sky, its brightness typically varies in a periodic fashion. This occurs because as an irregular object rotates, different amounts of illuminated surface area are presented to the viewer, and so the brightness decreases and increases, producing what is known as a light curve. Typically, once the object has made a full rotation, the light curve will repeat. This is how we can determine that an asteroid is rotating uniformly and how we can measure its rotation period. Now, let's talk about how objects rotate. For an arbitrary, irregularly shaped object, there will be a so-called principal axis, which has the maximum moment of inertia. And this acts as the North Pole about which an object may rotate uniformly. And as we have seen, an object in uniform rotation will produce a periodic light curve. The fact that the light curve is periodic tells us that the object is rotating uniformly, and the period tells us how long it takes the object to make one revolution. Now, objects do not have to rotate uniformly. In fact, if you try to rotate them about an axis other than the principal axis, they will go into a type of tumbling motion. Think of a football that's thrown in an imperfect spiral. It tends to wobble around. Tumbling motion is in general not periodic. That is, the orientation of the object never repeats, and therefore its light curve is not periodic. And we can use this fact to distinguish between tumbling objects and uniformly rotating objects. Now, what's interesting is that the state of uniform rotation is very special. Think about the example of the football again. To throw a perfect spiral takes a little bit of skill, because if you just arbitrarily throw an object or smack it with a baseball bat, it will go into a tumbling state of motion. Now, the asteroids certainly have been smacked throughout their history, and each one of these smacks would have imparted a random amount of angular momentum. Uniform rotation only occurs when the angular momentum vector is precisely aligned with the principal axis of inertia. So how come so many objects in the solar system are in this state?
Is that the point?
Well, not exactly, but we're getting there. Hold on. We need to talk a little bit about the forces that act on a rotating object. Think of the green ball here as a little piece of an asteroid which is rotating about the gray axis. As the rotation of the asteroid drags the little green ball through space, it imparts a velocity, the blue vector. The continuous change of the direction of that velocity vector creates an acceleration, the red vector. The acceleration vector is always pointed towards the axis of rotation. Let's make that a little more quantitative. Here's a side view of the same situation. Rho is the distance from the spin vector to the object in question, and omega is the spin frequency. You can show that the acceleration is omega squared times rho. And since mass times acceleration is equal to force, m omega squared rho is the force required to keep that little mass rotating with the asteroid. There are two sources of force. Number one, the gravitational attraction of the rest of the asteroid, and number two, any mechanical stresses due to contact with the other parts of the asteroid. For a uniformly rotating object, these forces will come into equilibrium, typically resulting in an equatorial bulge. However, for a tumbling object, the spin vector is not constant, and as it changes, so too will this inertial force m omega squared rho. It will change in both direction and magnitude. Since gravitational forces do not change, the only way to offset the change in this inertial force is to have a change in the mechanical stresses within the object. In all real materials, time-varying stresses result in energy dissipation. So, in principal axis or PA rotation, there is a well-defined north pole. The inertial forces are constant, so there are no time-varying stresses and hence no loss of energy as the object rotates. On the other hand, in non-principal axis NPA rotation, the north pole moves around. This causes the inertial forces to vary, so there are time-varying stresses and a resulting loss of energy, which leads to what we will call rotational damping.